So you see, this whole classroom is empty. And you know whose fault that is? The old guy. You see, he taught math the old way. You see, he kept out black way. A squared plus B squared equals C squared. Things that we learned before pre-kindergarten even became a thing. So, I'll do it the cool way. So today, we're gonna learn radicals. Imaginary numbers. But we're gonna learn them the new way. So let's hit up the lights. Okay. So let's see what we've got. Imaginary numbers. So, you see, whenever we have equations such as x squared plus 1 equals 0. Now this equation seems very easy to solve until we actually find that x squared equals -1 and x is the square root of -1. Now this is a problem. You see, this negative under the square root cannot be computed with real numbers. So let's say you have the square root of 4. Of course, the square root of 4 is 2. Why? Because 2 squared is 4. But when you have the square root of -x, no number squared will still give you a negative number. Obviously. So what do? So we created something called imaginary numbers. Of course, no mathematicians got killed during the invention of imaginary numbers. Just kidding, they did. So it was like terrorism in the mathematical age. So what do we have using imaginary numbers? Well, now you can actually solve the square root of -1. The square root of -1 is 1 times the square root of -1. So that would be 1i. I stands for imaginary, something you do in your dream. Now, let me advise you: don't think about this in your dream, or things get messy. You don't want to know how messy it gets. So you see, 1i. Let's do this with more complex fraction. -4 over 2, for example. -4 is the square root of 4 times the square root of -1 over the square root of 2. Now, of course, the square root of 4 is 2, and we know that I equals the square root of -1. So we just replace -1 by I. And of course, you can later radicalize this, but let's not waste time with that. Alright, so we covered the history of radicals and how many mathematicians got killed during its making. Second of all, we covered why radicals are, why imaginary numbers are, and why we need them in the first place. Now let's talk about the progression of exponents with imaginary units. Now you may ask, why is that name so long? Well, the answer is because I want to sound smart. The real answer, though, is that it's quite simple. Let's say you have I equals the square root of -1. We know that, right? Okay, what happens if we square I? We get the square root of -1 squared. We get -1. I cubed, you take I squared times I. Now, I cubed, you don't have to do I times I times I. That would just be too long. We take I squared, which is -1, and we take the answer, the product of I, which is the square root of -1. That would give us, of course, -I. So now you think, why should we progress along? It's just going to keep on going, right? Well, let's see what happens when we quadruple, when we put I to the quadrupled power. So that would just be I squared times I squared, and that would give us I squared is 1 times 1 is 1.
-1 times -1.
Oh yeah. -1 times -1, which would still be 1. Now, the thing is, you see all of these, this just seems normal. I is the square root of -1, I squared is -1, I cubed is -I, and I to the 4th is 1. The magic happens when you keep on going. So let's just write down what we have so far. So I is So let's say we have I to the 5th. That would just be I cubed times I to the 2nd power, right? So I cubed is what? -I. And I squared is -1. So this would just be I. which is the square root of -1. You see that when we go to the first power, it's square root of -1, second power is -1, third power is -I, fourth power is 1, and then we go back to the square root of -1 once we go to the next power. Now, this pattern keeps on going. In fact, we can investigate this pattern using a simple clock with only 4 numbers. First number would be I to the first root, which is the square root of -1, -1, -I, and 1. So, let's cover this up. So let's say you have I to the nth power. Any exponent raised to the which I is raised to. Divide that exponent by 4 and find the remainder and put I to that power. So, and we put I to that power. In fact, let's test this theory out. Let's say you have I to the 79. We divide 79 by 4 and we get the remainder of 3, right? So instead of doing all that computation, writing 79 i's, which I remind you is what the old guy would do, we just write I cubed. That's it. And we know I cubed is 1, 2, 3, -I. See, what we're actually doing is we're not just computing imaginary numbers, we're using modular arithmetic to help us do imaginary numbers. Now let's move on to some definitions. You see, every math class has to have a boring part. I mean, I said that I was the new guy, that I would do everything the cool way. And maybe I was just tricking you. Just kidding, whatever. Forget about it. You see, that's what happens when you script things. You get wrong and then you twist your leg and whatever. Now I just sound stupid for saying that. So, let's go over some definitions. Let's say you have the number 3. Now you would quickly assume that 3 is a real number. And you'd be right, 3 is a real number. Real numbers are all numbers that are not imaginary. However, 3 is also a complex number. You might ask why? Well, 3 also has an imaginary component, but it's 0, 0i. Even though it's 0, it still does have an imaginary component. So, therefore, we can call 3 and any integer a complex number. Now, we also have things called pure imaginary numbers. Pure imaginary numbers are simplified to, alright, so let's say we have a complex number, a plus bi. That's the formula. That's the expression for how all complex numbers are written. So a is the real component of the complex number, and bi is the imaginary component. So when you remove the real component of the complex number, we have bi. And bi is just any regular imaginary number. So this is imaginary. Now,